Hey guys, sound check, and the video check, of course. All good. Okay. Hey everyone who's already joined a little bit early. I saw that there's already quite a few people in there in the waiting room. We'll start in about 4 minutes. I was doing a sound check with the moderators. But already thank you for arriving early. There's already quite a few people in there, and sound should be all good. I'm hearing for the moderators. Thanks, Ricardo. Yeah, normally I go in 5 minutes early to do a sound check and a video check, but things are looking good. And you'll see me now, but later on I'll switch to the presentation mode. So I'll be off the screen. I'm still here, of course. It's a live webinar, which is pretty nice. Can be exciting as well if there's no network problems, etc. But if you have any issues with the quality, just let us know. Let the moderators know later on. Carlos is in the chat already. You see this. Welcome from me as well. We're a bit early. We'll start in a few minutes. We'll just wait a few minutes for the attendees to arrive, and I'll try to start sharp at 2:30 my local time. I'm here in Rotterdam at the moment, so I'll try to start sharp at 2:30. And I see some old acquaintances. James, I see. Hi, James. Theo, also welcome. There's GDPR ruling, so I should I can't call your last names, but hey, James, in the chat. Yeah, it's a long time ago. Indeed. Rob as well. I guess from Switzerland nowadays, Rob. I think I saw that on your LinkedIn profile. Hey, Rob. And we have people flowing in. There's still people coming in. There was quite a lot of registrations. We tried out LinkedIn for the first time, LinkedIn events. And in addition to the mailings that we sent, that was quite successful. So that was nice, very nice actually. Hey, Luc, and hi, Fitri. And Bart as well. Good afternoon. And Angelo. Oh, oh yeah, I see that, Theo. Yeah, last names in the chat, depending on how you enter yourself when you enter. And Meus as well. Good afternoon. We were just chatting, Meus, so that's it's fun to see you here as well. And Tijn as well. Hey, Tijn. Ferry. There's a lot of known names. Jonathan from Ecuador. It's getting a bit later there at the moment. And Gabriella. Good to be here, Gabriella, as well. It's 2:30 in Rotterdam, Central European time, sharp. And hi, Arend. You're still seeing me. I'm going to be here. It's a live webinar. I'm going to be here all the time, but I will switch to presentation mode, which means that um, I won't be in the picture, so to say, but it will be about the content. And towards the end of the webinar, again, of course, I'll switch off the presentation and I'll be back in view for everyone. I banked. Heala. I will be back in view and answering your questions. Carlos will actually, Carlos and Arthur are the moderators, and Carlos just popped a message there. Carlos and Arthur are moderating today, and they'll make sure that you have a smooth experience. And also try to answer questions as we go along. And answer those questions in the best possible way. But at the end of the webinar, roughly the last 20 minutes, there's a Q&A session. And in the Q&A session, I'll try to answer as much as possible of your questions, if I'm capable, of course, of answering them. So let me switch to the presentation. So I will disappear from the screen, but I'm still here, and I'll be back towards the end. Again, everyone, welcome to UReason's webinar. Before we start, some important details. Carlos already pointed it out. Carlos and Arthur are supporting me in the background today as moderators. If you have any questions, please feel free to contact them. And of course, if you have any thematic or technical questions, you can ask them during my presentation. And Carlos will collect your questions, and I will answer the questions all together in the Q&A session towards the end of the webinar. Our webinar today is about predictive maintenance. The title is The Myth of Predictive Maintenance. I will try to shed some light on the topic of predictive maintenance from our point of view, and of course, as always, using concrete examples from our projects. And I will look at predictive maintenance from the market point of view as well as how we communicate with our customers and as we hear it from you and from our partners. I'm Jules Ootmans, presenting to you today. I have a background in AI starting in the 90s, and I've been involved many times in the past 25 years in prognostic and predictive programs that ensure asset integrity for critical assets and critical processes. I've done this in different industries such as oil and gas, petrochemical, chemical, and paper, and my work has always been focused around using the data that's available, both streaming and historical data, to provide better understanding of what is happening in the process, i.e. what is happening now and what is expected to happen to the process and the assets supporting the process in the future. Here are my contact details. If you have any questions after the webinar, don't hesitate to contact me and to email me. I work at UReason, a Dutch software company that provides solutions for real-time condition-based and predictive maintenance. And I help our customers daily to use our software, from data analysis to the setup of applications and solutions that monitor important assets and optimize processes. At UReason, we combine our domain expertise and software knowledge with our customers, and I help them daily from data to solutions. We have offices in Rotterdam, which we see here in the picture, and Reading in the UK, and our customers are predominantly in the manufacturing and process industry, and the majority of them are located in Western Europe and the North Americas. UReason is active in the real-time condition monitoring, predictive and prescriptive maintenance domain. Our field of operation is from helping customers to insights in data, to helping asset owners, OEMs, and maintenance services organizations with data-driven maintenance solutions. Often we start together with our customers to define the business case and the use cases to focus on. And very often this also implies a new strategy for the customer, especially if our customer is an OEM. Once the business case is defined and use cases are clear, it's typically followed by data collection, data verification, model development and deployment. And the deployment is of the solutions into the existing OT and IT landscape. Our software APM Studio is used at different levels in the automation pyramid, embedded with OEMs, monitoring faults and risks in isolation to the asset. And an asset can be instrumentation, an actuator or pump, a compressor, a filter, etc. And OEMs often use our software APM Studio as a basis for the remote monitoring services solutions at the device, edge, and cloud level. At the edge, APM Studio typically processes asset data of one or more assets to run condition monitoring and predictive applications near to where the data is actually generated, enabling horizontal integration across the assets. But we also work at level 2 and 3, where APM Studio is used to monitor faults in relationship to the process deployed and running on on-premise compute. When we deploy at level 4 and level 5, APM Studio is used for optimizing the maintenance costs and planning associated to an asset base supporting the process. We serve two types of customers. We serve OEMs, where we help them to maintain the margin on their products that they bring to the market, or allow them to create and integrate diagnostic and prognostic data from their assets into the systems of their customers, or enable them to provide new digital business services and business models on their assets. In short, allowing them to stay relevant for their customers. And we work for asset owners, where the challenges are around lowering the costs, energy costs, maintenance costs, reducing the amount of planned maintenance and reactive maintenance, and enabling them to stretch the asset lifetime while balancing the risk and optimizing their planning. The OEM sees their asset as the value, and the asset owner sees the asset as a value supporting the process, or the process that they're running, and the outputs. So why do we do what we do at UReason? Well, around 95% of the data from instruments, machines, and processes is not used today to optimize maintenance. This is our understanding from hundreds of conversations with operators and manufacturers. The operational data from process and instruments is used, of course, to control processes, monitor processes, run processes safely, but not to optimize asset management, work processes, and to support maintenance. And this is our driver. This is why we help asset owners and OEMs to achieve more potential from the data that they already have. And we do this every day with a lot of passion. Now, before I start with the main part of the webinar, let me ask you a question to understand where you stand on the topic of predictive maintenance. And I'm going to start an interaction, and that interaction will pop up in your screen. And if you can indicate by selecting one of the choices where you currently are you at the beginning, orienting yourselves and informing yourselves about predictive maintenance, or have you already gained initial experience in pilot projects, or test projects, or MVPs? Or is predictive maintenance perhaps already an integral part of your maintenance strategy? And I'm looking at the responses. There is the majority of you have already gained initial experience in pilot projects. That's quite nice, because I will also discuss and spend some time on typical failures that actually happen in pilot projects. So the responses are still coming in. It's going, wow, it was going head to head, the first choice and the second, but about 49% of you have already gained some experience, and 38% of you are at the beginning, orienting yourselves and informing yourselves on the topic. So I think for both, actually for all the groups and all the responses, I think this webinar will be of interest to you. Let me close the interaction, and there's still answers coming in. Let me close the interaction and proceed to the webinar. Thanks for your inputs. So with the short introduction of UReason and my first question to you, let's go straight into the topic of today's webinar. I will try to guide you through the topic of predictive maintenance in a myth-buster way, analyzing with you if predictive maintenance is a myth or a hype. I'll try to do that using the Gartner hype cycle as guidance, and I think most of you are familiar with the Gartner hype cycle. Nevertheless, let me briefly explain what the Gartner hype cycle is. So the hype cycle is a description of how technologies develop over time and are adopted over time. And it applies to new technologies, especially digital technologies. The cycle of adoption starts with technologies coming from innovation and coming from the innovation trigger upwards. And you should hopefully see my mouse pointer here. Um, the expectations that are created by talking about the innovations of the technologies exceed um, um, a realistic level, because there's a lot of talk and a lot of hype about this. When this happened, you reach, or you actually meet, the peak of inflated expectations, which is the peak here in this in this graph. Here, there are a large number of projects are started, and many of these projects are not completed or are not delivering the desired results. And here also comes the realization that maybe everything is not so easy after all, and the initial expectations were exceeded. But you started a lot of projects, you tried a lot of things, you tried a lot of projects, and the lessons learned are used to approach the whole thing, in our case, the topic of predictive maintenance, in a more realistic way, and to bring the technology bit by bit from the disillusionment through the alignment phase into the productivity area. I will now try to classify predictive maintenance on this Gartner hype cycle on the basis of various insights from our projects and customer interactions over the past years, and also share some examples. So our observations in talking to the market and keeping up to date with market research, etc., have shown 5 top digital trends in the field of maintenance. Number one, the contractor portals, digital portals to work together with contractors and subcontractors on work orders, jobs, streamlining the work order data across multiple stakeholders and actors. Number two, the maintenance dashboards. Dashboards for the sharing and analysis of maintenance data, insights into how many jobs are outstanding, top jobs from a spending point of view, and providing you with insights in bad actors. Number three, handheld, mobile devices, mobile maintenance, using mobile devices to record and make available data directly from the field. And number four, remote expert systems, which are extremely exciting systems. The keyword here is augmented reality, mixed with reality and smart glasses that we see here in the picture to assist field personnel in executing their work. And of course, there is topic number five, data-driven maintenance or predictive maintenance. Now, in our opinion, these are not the top 5 trends in maintenance. They're not the top 5 trends in maintenance from the discussions, the projects, and the work that we do on a daily basis. Let's take a close look at predictive maintenance in the hype cycle. So we are in the Gartner hype cycle with predictive maintenance at the innovations trigger. The topic is known, people are talking about it a lot. And let me ask you a question again on that topic, because you joined this webinar, so you also have a certain interest in predictive maintenance. So one of the polls should have started again in your browser. Let me know why you are interested in predictive maintenance. Before I continue, I mean, you may be interested because you heard a lot about it or read a lot about it, or you may be interested because you have already made a choice to make your maintenance activities more predictable, more plannable, or perhaps you want to develop new services for for your customers, for our customers. And there's a lot of response already that came in. At actually, front running is that most of you want to develop new services for your customers. So you may be an OEM if you provide that answer, or an MRO, or a services provider if that is the goal for your interest in predictive maintenance. And it's going head to head with wanting to make maintenance more predictable. So I think that's the response that comes from a lot of the asset owners. And there's also a part of the audience that hear a lot about it, read a lot about it, and want to learn more about it. And this webinar will help. So stay on, and let me take you through the story around how um, predictive maintenance is not a myth. So again, thanks for your answers, by the way. And actually, your answers, looking at it, actually confirm our observations. That's the observation that a lot of people are talking about it and want to learn more about it. And we do a lot of webinars at UReason. And after each webinar, we also ask the audience what topics they would like to have covered in the next webinar. And predictive maintenance is in demand here by far greater distance than other topics with the people who attend our webinars. So there is a significant interest in the topic and a significant interest in also the subtopics that enable predictive maintenance, such as edge computing and applications. If actually it brings me to another observation. We have a library of about 35 webinars at the moment that we've given since last year, and today's webinar, the myth of predictive maintenance only, and only looking at the names and the companies and the number of registration is by a factor 3 the webinar in which most of the people are interested. This webinar has nearly 400 registrations and a lot of viewers. I haven't looked in the panel yet, but there's a lot of viewers. So there must be a genuine interest. But whenever I'm interested in a topic, regardless of whether it's new or old, I tend to go to Google first, and I think that many of you do that too. So, in preparation of this webinar, I sat down with Google and I asked what the potential is of predictive maintenance. And I went through the first two Google result pages and searched specifically for the potential and the purpose. What does predictive maintenance bring in terms of savings and increased availability? And I've just stopped after 10 results, and you can see here in the picture in the table the savings. It's somewhere between 10 to 40%, and savings are in maintenance through predictive maintenance are promised or discussed. And a similar picture emerges with increased system availability. Yeah, the third column here in the table. So the added value of predictive maintenance that is discussed on the first case of the Google results is substantial. And that is to say the least, of course. If you read through these reports and blogs and studies, a few things are immediately noticeable. The first is what are the savings, a percent related to what? As it's always in relation to what that actually counts. What do I save 40% on? It's very important. Do I save 40% on purely reactive maintenance activities or planned maintenance? And the second thing that stands out is that the figures for savings in maintenance costs and system availability, these are always shown nicely side by side, availability going up and maintenance costs going down. But of course, you know that this potential is increased if the availability, let's say, is increased by 25%. It's quite logical. And the third thing that stands out is when you go through these results and reports that are out there on Google. There's simply a lack of use cases, references, and concrete examples that guide you through and explain how these customers, these companies actually achieved all these benefits. So, taking this back to the Gartner hype cycle now, using the three perceptions that I discussed and all the buzz around it, we're at the very top of inflated expectations. 40% savings, maybe 25% more availability. There are gigantic values to be earned doing predictive maintenance. Before I go any further, let's take a quick step back and look at the different technologies that have been out there for a very long time. If you look at predictive maintenance more from a technology side of view, then of course there are technologies such as thermography, oil analysis, and associated particle analysis, visual inspections, inspections with ultrasound, sound measurements, and a whole range of other technologies that fall into the area of predictive maintenance. These are all predictive maintenance technologies that help you to assess the condition of equipment and assets and to plan maintenance based on the condition measured at a specific point in time. And of course, we shouldn't forget to mention vibration measurements here and vibration analysis, of course. Here are a few examples from our office where we're currently configuring devices for customer projects. Vibration analysis, of course, mostly applied on rotating equipment, rotating critical equipment, is a field that has been out there for a very long time. and can roughly be divided in two different types. The first is rather simple vibration analysis, where you just measure the acceleration. And if it vibrates too strongly, it triggers an alarm. And of course, the second category, the more complex vibration analysis, is the analysis of the frequency spectrums, where you target certain frequencies in order to identify the cause of errors at an early stage. These are all technologies and approaches that fall under the umbrella of predictive maintenance. But if we look at the conversations and the projects that we're doing, the conversations that we have with customers and partners, and the projects that we carry out, the large majority, 99.9% of these conversations are actually not about the technologies that I just showed, but always about using the data, mostly the data that comes from the instruments and actuators that are already out there present in the field. As I already said earlier, this is 95% of the data that is already available and can be used with AI in such a way that errors can be recognized ahead of time. So that's the area we mean when we talk to you about predictive maintenance. The other technologies presented are excellent technologies, of course, which have their raison d'être, and which we have been using successfully for decades. But let's have a look now at what it actually means and how does it actually work using the data that is already available from your assets. So I have an asset that produces data, and sure, every asset produces an infinite amount of data that I can save and record. And an asset is maintained, and if I do this well, it also records what maintenance data or the maintenance data, what maintenance activities I carry out, and for which faults these were carried out. For example, here I have nice timestamps of when a certain error occurred and what was broken. Now, of course, I can go and link these two data sources together, i.e. the essential data and the maintenance data. And with the timestamp, I can precisely assign data in my operating time when I had certain errors. Now, this is a simple example. I'm deliberately too provocative. So let's assume now that you want to solve this and you're technically interested but have no programming experience. You can start to combine the maintenance data and the operating data, and you could start to train an algorithm. You could spend the morning to learn Python and familiarize yourself with looking at a few YouTube tutorials in the afternoon. And after a day, you're ready to actually train a machine learning model that is able to predict the errors from this data and then to create the alarms for your maintenance personnel accordingly. Every error, as shown here, for example, leaking for A or broken, has a certain fingerprint in the operating data. And this fingerprint can be learned using a simple algorithm. And as soon as the fingerprint is recognized, an alarm can be generated. There's two important factors here. The first is how quickly, before such an error really occurs, can such a fingerprint already be recognized? And this may take, maybe seconds or months. It also always, of course, depends on the application, whether that is really enough. Is it enough if I can tell a minute, 5 minutes, 10 minutes in advance that a problem is coming? Or do I have to know this a week in advance? Then there is the accuracy of the algorithm. It is never 100%. It has a certain validity. And in both cases, errors are not recognized. However, false alarms are also issued, which again depend, of course, on the use case and the business cases. How many false alarms can I tolerate, and how many undetected errors can I tolerate? That's always the question. So, such an algorithm can deliver real added value for me, but so far so good. As I said, it is really simple, and we also train customers to do this. We usually train our customers in the usage of our software APM Studio plus data analysis for about 12 hours. But if you learn it yourself with Python, that's a day's work. And if the data is available, well, maybe it's not that easy after all, because problems arise when you really start projects like this. For example, one looks at the maintenance cost, recognizes timestamps, and completely and sees that they are completely useless. The timestamp of the errors is not noted, but the timestamp is noted when something has been entered into the maintenance management system, the data entry. And so the data entry for timestamps is very often completely unusable. And this is one of the classical, I would say, classical mistakes. A second classical mistake is the reason for failure is unknown. We see that 80% of the maintenance data is not properly registering the cause why something failed, or the resolution, how things were fixed. Yeah, and I may know that at some point in time this week there was X and Y and Z issues, but I don't know what kind of cause it was, especially not if it was 5 years ago. And the third classic problem is the data is saved and available, but maybe saved with the wrong resolution, a resolution update frequency that is too low. There are projects where we find process data that is saved once every 8 hours, and it was decided that way many years ago. But there's not so much that can be done with this data. And these are the typical three mistakes that typically summarize a first project. In a second project, if you want to deal with this yourself, you will learn from your first mistakes, first project, and make sure that the data is in order and available. And you put a lot of effort into correlating data with each other, perhaps with a little bit of text mining, only to finally come up with a result that everyone already knew for a very long time, and can be tackled in a deterministic way. So you find relations, causalities in the data that were quite obvious. And yeah, your third predictive maintenance project may also not be a success either. And you've come to a point that you can predict a failure or leakage 25 minutes ahead of time, which is technically wonderful, but unfortunately neither on the side of the operator nor on the part of the project team, the maintenance team, it makes any point to ask whether it adds any value. Knowing this 25 minutes ahead of time, if you can't react to that, then it doesn't have any value at all, because you can't integrate it into your current work processes. So you in the audience may already have had similar learnings, and yeah, these learnings, taking that back to the Gartner hype cycle one more time, cause disillusioned projects, and perhaps many more disillusioned projects that definitely had a potential value, but led to a disappointment because the data quality, unlocking the data in the right resolution from the systems was not that easy. So we recognize that there are situations that can save 20% on maintenance costs and get 30% more availability, but the whole thing isn't that simple after all. As always, the devil is in the details. So how do we proceed in a way that is more successful? Now, you have to realize that predictive maintenance projects are actually like a brick wall. One stone on top of the other, and every stone is important: data algorithms, IT, security, interfaces, etc. And these projects can be infinitely complex, and this brick wall is littered with problems, organizational problems, financial problems, problems related to the fact that digitization is at stake and the emotions that it deals with it are quite high, integrating the OT and the IT world. And yeah, this wall, with all its stones and all of its overlapping problems, you lose track of things relatively quickly. What are we doing? We start, when we do projects, we start with a motivation. We ignore everything else for now, and we say what the motivation is to do a predictive maintenance program. Here for this equipment, for this subsystem, or for this unit, for whatever. And the second thing that we do is we just accept that the environment is there that it needs to operate in. So the second thing to be concerned about is, what do we do with the results? Um, This is not a trivial question. In 50% of the cases, the answer is that little can be done with the result. It doesn't matter if you realize beforehand that equipment is breaking. You continue anyway because the process, the organizational processes are not capable to respond at the right time in such a short time, or you would have to reorganize and rearrange organizational processes in order to adapt production, production planning, and maintenance. So it's not that trivial. Going back to the motivation, step one is always to draw the motivation straight. Yes, it's called predictive maintenance, but what we actually want to do is make maintenance more predictable with data. I don't care whether there is an AI or machine learning algorithm or a new sensor or an edge device. The aim is to ideally make maintenance more plannable with existing data. And the second important point to deal with from day one is to assume that maintenance can be made more predictable. If you can do it like that, it can work, and it can work for you. And if I manage to integrate the results of a program, a predictive maintenance program, back into my work processes, I will be able to rearrange my work processes so that I can integrate the results. And to point it out again, very often it really happens that one develops predictive maintenance algorithms for individual isolated assets. There's an alarm that the asset fails in 2 weeks, but in the broader context of the production process, this information is worthless because I cannot integrate it. So always include step number two after the motivation, how to deal with the topic, how to deal with the integration of what you want to do into your work processes. Now, let's look in detail at what this actually means and how. How do we implement this in practice in our projects with our partners and with our customers? In front of you, you see a simplified workflow of a maintenance work process. From the top of inspection or from the breakdown to the end, the closeout. With planned maintenance on the left-hand side, and of course, the unplanned maintenance that can be introduced by predictive maintenance and condition-based maintenance models. These inputs from CBM and PDM models may lead to notification or, in certain cases, automatic work order creation. And a large part of your asset-based inspections can easily be automated using the data that is already present in your assets, the diagnostic information from your instruments and actuators that very few companies step into, and we do not understand why they don't. Of course, in the past, there were limitations to process and store the data, but this is really gone now. And there are many simple ways to make maintenance more plannable using the data that you already have, and of course, next to the more advanced approaches using causal models, probability, and machine learning models. Unlocking the data from the field level also has become much easier nowadays and much more accepted. Where 20 years ago, we would normally tap into the data historians to access processes and sometimes asset data. And in certain cases, we would integrate this directly at the basic control level. In cases, we would also apply control on the basis of the outputs of the model. And we've seen more and more now that customers are allowing us asset data to be extracted in parallel fashion, i.e., not passing through the automation layers, but and through the pin and the mesh layers, but coming straight from the field in a digital and secure manner, which follows the more open architecture fashion. Now here, edge compute, small cabinets, mounted computers are making our lives a lot easier, providing access to a lot more data that does not have to flow through the automation pyramid to be of value. And we can run root cause analysis models very close to where the data is actually generated. Now, let me ask you another question. Let me start another interaction. So bear with me a second. And the question is, what are the biggest hurdles for you when you're introducing predictive maintenance? Is it missing data, organizational changes, OT to be integrated with IT, the lack of business cases, the development of algorithms? A lot of people think it's complex, but yeah, we believe it's quite straightforward. If you know what you need to do, you need to have classification and regression models. Or is it maybe the time to deal with the topic that the degradations are so fast that you cannot deal with the topics in a very fast way? Or yeah, maybe that's also possible. You're missing use cases. That could also be a case. And I'm looking at the answers coming in. So a lot of you identify organizational challenges. So this is could be on the OT, IT area. It could also be in the area where reliability engineers, maintenance engineers need to become more data driven. So an organizational challenge is sometimes training of people. Actually, this is led by missing data. I think a lot of the asset owners have a lot of data, but it's not being unlocked from the machines. And then it's followed by the business cases, no added value. So yeah, if you don't have a business case, if you don't have a motivation, it's hard to do a PDM program successfully. Again, thanks for your inputs, and I see there's also some questions, and I received some chats as well. Thanks, Mayers. I noted that typo in the sheets. um, it's not progressing. There we go. Again, thanks for your input, and let's have a look at some examples. So here we see a system, or a small part actually of a system, that oversees the output of important flow meters in the process, and the motivation is to keep an eye on the accuracy of the instrument. The model, in this case, a machine learning model, regression model, replaces the measurements when needed, and when needed is, for example, when the EMF meter has fouling or sediment buildup, and a work order is automatically sent to the CMMS system when this happens too often in time. Another example is, for example, monitoring the lubrication system of large turbines, where we use cost consequence models. We determine the likelihood of the failure, and the motivation here is knowing what is going to happen in order to balance the risk and tie this back straight to the operational planning and personnel. And this is also true for the third example that I'm showing here, monitoring process lines, pipes, to prevent process upsets and find the ideal time window to actually pick the lines. All of these are examples that we have done in the past, that we're currently working on, some of them in the past, where data is being used to make maintenance more plannable. Another example, an anonymized example of monitoring pumps for different failure modes, keeping an eye on a multitude of different failure modes that are developing, and an actuator example. We basically do a lot for OEMs and asset owners on small motors, large motors, but also in different industries on robots, where things are still data driven. And in production cells, again, a different industry. At the beginning, I actually showed what Google says when you look for predictive maintenance and the gains for predictive maintenance, and what can be done with predictive maintenance in the terms of savings and availability. From our point of view, it's difficult to validate these results. I will summarize what we know. So it's, for us, difficult to validate the results of Google, but I will summarize what we know. Now, on average, when we work with operators, we find around 10 data-driven use cases in use case workshops that make sense per 100,000 euros of savings or revenue increase. Of these, I went forward. I didn't want to do this. Apologies. So of the 10 use cases, 3 to 5 use cases are in maintenance, and the other use cases are more operational process use cases. And if we find 10 cases, there are almost always 10 positive use cases where we typically are cash flow positive in 6 to 12 months, i.e., after 12 months at the latest, there will be more savings than what was actually spent or invested. And after 12 to 18 months, you are typically, or we are typically break even. That means that you earn more than you actually spend in total. And we're always trying to generate a cost benefit ratio for our customers of a factor of 5 to 10. So that means um, when you're out of the pilot phase, every project which is operationally running at the end of the year should bring 5 to 10 times more than it actually cost. And we know this is possible. And as we actually see this in our projects over the last years, that these can be quantifiable results of predictive maintenance. Now, if you put this in relation to our hype cycle, the Gartner hype cycle again, I would like to say that we are definitely in the transition from the enlightenment phase to the productivity phase. So that means that you no longer do pilot projects like crazy, but rather go after very specific projects which have a motivation that can be tied back into your organizational processes. And you can be successful in your projects with a proper motivation and this tie back. We see more and more projects being put into the predictive use, where predictive maintenance is used on a daily basis to make maintenance more plannable, more predictable. Now, and I'm keeping an eye on the time as well because I've overrun by a few minutes. Let me summarize the main points for you. Um, First, predictive maintenance is all about making maintenance activities more plannable using data. Secondly, it is very important to integrate the results from a data-driven predictive maintenance program back into your work processes. If you don't, you run the risk that adoption and value earned is low. Most importantly, the third point, predictive maintenance is not a hype anymore. And I have some specific advices, summaries for you in the audience if you're an asset owner. Become data aware, find good partners, and work with focused, relevant pilot projects and rollouts that use the data that you already have to make maintenance activities more plannable. And some specific advice for the OEMs in the audience. Data can be translated to euros. The question is not, does your customer pay for it, but do I want to stay relevant to my customers with your current and future products? That's the real question for the OEMs. Now, this almost concludes the webinar. For those in the audience that want to get a thermometer for their organization, where they are with respect to data-driven maintenance and how you can improve, I invite you to our website to run through the data scan. The scan is free, takes you a few minutes, and provides you with valuable insights and advice on where you stand with your organization with respect to predictive maintenance. And we will share the slides. We always do after the webinars. And this slide is clickable, so you can just click on the slide and it will take you to the website. I would also like to invite you to our next webinar, which will be held together with Focus On, which is a joint venture between Krone and Samsung, two German companies. This webinar is held on the 16th of December, and in the webinar, we will show you how you can advance asset management with smart devices in the field, like the Focus One control valve. And this valve that we see here in the picture in the bottom left actually runs our software embedded to provide diagnostics, control, and prognostics, making maintenance more predictable and plannable. Now, that concluded the webinar. I'm a little bit over time, I see on the clock. And let me check with Carlos and Arthur what the questions are. And here again are my contact details. If you'd like to reach out to me, scan the QR code and I'll get back to you. and I'm going to switch now to the camera view. So I'm still here, and I'm going to check in the presenter chat with Carlos. I apologize a little bit for being a little bit over time with the questions, and they're flowing in, and they're being nicely numbered for me. So I'm going to read out the question and then try to answer it. First one is from Peter. From which maturity level can PDM be introduced? So which maintenance maturity level? Now, if you have a good motivation, good cases, predictive maintenance can be introduced at customers, with customers that have a very low maturity level. So you don't have to have your house in order with respect to data collection, problem calls, remediation codes that you're registering in your CMMS system. You can already start with the data that is already available in your process automation systems, from the field level up to the control PLC level up to a SCADA or DCS level, if you have the right motivation. So if you want to, for example, reduce the number of inspection rounds, but you don't have a good recording of inspection results in your CMMS, it doesn't matter. You can already start with predictive maintenance at a low digital maintenance maturity level. I hope that answers the question, Peter. I'll go to the next question, which is from UReason. Are challenges for predictive maintenance for smaller SMEs comparable to large factories? I think in the challenges that small and medium enterprises, SMEs, have in respect to very large ones like the Shells and the Chevrons, etc., of this world, I think the challenges are the same. I think smaller companies typically are much more agile in reacting to issues that they have with their assets, the amount of reactive maintenance that is being carried out. In larger companies, of course, predictive maintenance programs are typically rolled out in a much more corporate central engineering type fashion, where every site tries to do things in the same way, so that you can benchmark across typical assets, centrifugal pumps of a certain manufacturer across multiple sites. So the challenges are the same. I think that there is a benefit for larger companies, especially when it comes to benchmarking across other sites, because data sharing in industry is still a bit of an issue. Although there are developments in this area with international data spaces, sharing data and being rewarded for sharing data is still something that has little adoption in especially in process industry. I'll jump. I hope that answered the question, Jurjen. I'll go to the next question from Jonathan. Is it possible to develop PDM models if not enough labels exist, alarms, breakdowns, failures, e.g., a couple of events in the year versus a whole year of data captured by sensors? Now, yes, I'm going to answer this question. It's a long question. So, is it possible if you have not a lot of label data? So, label data, when you start training machine learning models, classification models, for example, to recognize a certain failure mechanism, you need to label your data to identify how the supervised machine learning model can actually recognize that condition. And if typically you use alarm event information from your assets, from your processes, as a labeling mechanism, operational labeling mechanism, to label your data, and then you complement that with the data that comes from your CMMS system. So inspection results, and maintenance activities, and PCR codes, problem calls, and remediation codes, if these are recorded. Now, very often what happens at our customers is that especially the CMMS data is insufficient, and that causes you to have not many labels about operating states and operating conditions. And there we have an approach where we look if they are available at the FMEAs and FMECAs, and on the basis of the failure mechanisms, we start what is called feature engineering. We start to add additional labels that classify the existence of specific failure mechanisms that lead to failures in the data, such that even if you have very sparse label data, so not a lot of label data, you can still make a step with machine learning models going forward. But we always combine these with, in our bow ties in APM Studio, with engineering knowledge, where we have cause consequence models that use engineering knowledge in combination with machine learning models. So if your machine learning model is too imprecise, so for example, that only has an accuracy of classification of, let's say, 80%, we typically balance this with engineering knowledge inside bow ties to still give you a proper identification of the likelihood of a certain failure mechanism taking place, and a proper indication of using survival analysis of when that is about to happen. I'm scrolling down. Another question from Urian. What is the ratio of costs, hardware versus software versus data science in FTE? Ooh. Um, Now, the hardware, I think you should always start on the basis of the data that's already available. So very often, if you don't want to do a pass-through through your automation system, you have to create this second channel and a Nomura open architecture compliant channel to unlock the non-process automation data. So the data that you have, data that goes to your SCADA DCS system for control and monitoring purposes, and you have diagnostic data that you also want to unlock. So there are some hardware costs involved in serializing remote I/O, providing edge computers, having edge computers locally in cabinets, especially if it concerns unlocking high frequency data. And if you want to do everything on premise, there's also some hardware cost involved versus doing it in the cloud. There's some cloud subscription cost involved, of course. I think the software is similar as the similar component as the cost for the hardware. It's a cost you take, and we provide different software subscription models, asset based, IO based, but we also have CapEx models for our OEMs to kind of balance that, and we think along with our customers in that sense a lot. So I think software costs can be balanced along with the hardware costs. Now the data science really depends on the amount. So the data science cost really depends on the amount of um, knowledge that's already available within the company about specific failure mechanisms and failure modes. And if you start, let's say in a greenfield, you don't have knowledge about how the process operates, etc., then the data science cost may be a factor 5 to 10 of the hardware and the software costs. If you start from a base in a brownfield where you have FMEAs, FMECAs, maybe some RBI results, you have a CMMS that is filled, you have historical data, then data science can also be automated to a large extent with auto ML, auto machine learning. There's a number of packages that provide that help you in establishing the right models. But I would always start with cost consequence models because they are quite powerful. We have bow ties for these to explain to the user what is going on, what the likelihood is, what the causes are, and what the consequences are if they don't react. Question from Theo. I hope that answered the question you're in. It was a difficult question. Question from Theo. Time-wise, when do OEMs contribute to asset owner ID conception, if at all? Will one be too late once the requirements are defined? Yeah, so Theo, I think I know you're working for a drive company, a German-based drive company. So the question is, when is the OEM relevant for their end customer, irrespective if this is an asset owner or another OEM? Should it be at the idea conception, helping their customer with the ideas about predictive maintenance, or should it be already in a product design phase if it concerns an OEM? I think um, uh, it I think time-wise it doesn't matter. There are quite a lot of OEMs that provide products based on your product, Theo, to the market. I think it's the Theo. I don't see your last name, but I assume it's the Theo. But um, um, there is there's an advantage if you help your OEMs and your asset owners along the path of making either their processes more cost efficient and more plannable, or your OEM's product deliveries more complete. So there is no, I don't think there is a specific time at which you need to be on board. I was talking earlier today to a consultant that works in the feed for a large petrochemical facility in the feed stage, and it's a very early stage of a greenfield installation. Is it too early? Is it too late? I think it's at the right time, because then you can take the data communication into account by design. I'm going to go to the next question, because there's still a lot of questions coming. A question from James. You mentioned the importance of being data-driven and data-aware. Do you have any observations or advice around how long the data should be kept for, e.g., future ML projects and analysis? Now, many years ago, my first AI project, early 90s for Exxon, was using data from a Olivetti DCS system, water cooled. Data was stored in a mainframe, and it was very expensive to store the data, and it was very expensive to get the data from the mainframe. And so data was a hurdle. Keeping data for a longer period of time was a hurdle. Now nowadays, I am of the opinion, but that's my opinion, that you shouldn't throw away data. As long as you can ascertain what the context was in which the data was generated. So don't throw away data that is statistically irrelevant, like states, statistically irrelevant, like the feedstock or the feedstock quality, etc. It's data that doesn't change very often, and is very often forgotten to be also historized for a longer period of time. So my advice around keeping data is to keep data for as long as possible as time. And then you have, of course, with many providers, you have hot storage and cold storage. Hot storage is for data that you want to use in analysis ML pipelines multiple times, and that you access quite often. Hot storage, of course, comes at a slightly different price than cold storage, but in both cases, retaining data is not such an issue anymore. And on a personal note, 2 weeks ago on the weekend, I got myself a new SSD for backing up my photographs, etc. And a 2 terabyte SSD only costs 150 euros. And it's remarkable, because when UReason started 20 years ago, 2001, we did a project for BG Transco, for the British gas network, and storage at the time was still roughly around £1 million per terabyte. So we went from £1 million per terabyte 20 years later to 75 euros, let's say £70 per terabyte, which is incredible. So the cost of storing and retrieving has gone down dramatically. I would advise to keep as much as possible. I'm going to go to the next question from Desman. What kind of approaches do you use for developing data-driven models, supervised or unsupervised? And how do you manage to isolate the fault? So we typically, for predictive maintenance projects, we try to identify the different P's on the PF curve. And the P is potential failure, the F is failure. But the potential failure is what you want to be aware of, and then start to predict the actual time that you still have to when the failure occurs. Now, failures do not occur very often in the process industry, in safety critical industries, because asset owners will try to prevent them, operations will try to prevent them, and safety systems will prevent them. So there won't be a lot of failures happening in your data as such. So instead of failures, you have to look for dysfunctions. Dysfunctions are events when the asset is not performing as it should be anymore. So from a efficiency point of view, energy consumption point of view, output point of view, etc. Coming back to your question, the first question, do we use supervised or unsupervised? Because we're dealing with the fact that we want to be aware where we are, we use supervised machine learning models. And we isolate not the faults, but we isolate the failure mechanisms inside the data, sometimes with feature engineering to train the models. Unsupervised machine learning is also quite valuable, but it has its own purpose. for example, training a model to recognize training a model on the data of the last month in order to recognize any deviations, and then to have a feedback loop with the user to actually identify what those deviations were being caused by. Because unsupervised machine learning is good at clustering, but not very good at precisely saying what's going on. I hope that answers your first question, Peshman. And I'm scrolling down. There's another question. Are your approaches applicable to non-stationary processes? Oh, I'm not sure what you mean by non-stationary process. So we work on static and rotating assets in different industries. I'm not sure what you mean by non-stationary. I think by processes that are non-static, i.e., are fluctuating a lot depending on the feedstock, conditions outside, etc. Yes, the approaches are. You need to take into account the features in the environment that are of influence to the degradation and the dysfunctions that you were trying to classify. I'll go now to the next question from Ti Yao. I hope I pronounced it correctly. How long is the transition from innovation to dissolution and finally to the productive stage? The danger is at dissolution. It might be to abandon since it starts as a project. Yeah. So the transitions from innovation to dissolution, I've seen this in companies. There's no one answer for this. I've seen companies that have spent 3 years on predictive maintenance pilots and have spent a lot of money and um, spend a lot of money and are continuing because it's loss of face, there's politics, there's all kinds of other reasons. I've also seen companies that have a more agile approach and they say we are going to try this approach. If we're not successful, we'll stop after 3 months. So we typically, in our projects, we have a very gated process where each stage of the project and delivering a solution to the customer, we have a set of criteria and we try to keep the stages of the project short, 2 to 6 weeks maximum. And at the end of each stage, during and at the end of each stage, we always look back at the criteria, the evaluation criteria that we agreed upon with the customer upfront, and determine if we can go to the next stage in order to prevent dissolution and in order to prevent projects to take too long a time. So there's no one answer to your question, Tiao. It's very customer, very organizational dependent, but our advice is to keep these projects sweet and short. And let's see, a question from Jurjen. Have you experiences with ML model drifting after implementation? Absolutely, Jurjen. This is once you deploy a machine learning model, it's we have other webinars, but also training for this. Once you deploy a machine learning model, it was deployed on the basis of, let's say, historical data of the last year or the last 2 years, whatever. But over time, your process may be fouling. There may be different materials that you're using, different people that may be running the process, different control regimes, different control settings that are actually of influence to the output of your ML model. So we always keep an eye when we deploy ML models in our PMML engines on the accuracy of the ML model. And if the accuracy is below configurable thresholds, then it is fed back into a data science loop to get updates on the ML model based on historical data. You could also automate this process, by the way, but I did this in the late 90s. There, in automation of that process, you always have to be careful that there are no features omitted from the process that are of influence to what you're trying to classify or trying to predict. And I'm just looking. Oh, Arthur already answered part of this question. Thanks, Arthur. I'm a little bit over time, 3-4 minutes. Again, thank you for attending the webinar. Thank you for all the questions. I am getting the being pinged that I need to stop. So next time I'll try to be a little bit faster in the slide or have less slides. I think that's the solution. Again, thank you very much from my side for listening and asking the interesting questions. My contact details are in the slides. Don't hesitate. When this webinar stops, there will be a evaluation form, and we really appreciate your feedback. Also, your feedback on what topics you would like to have addressed next. And so there was a link earlier on for the people that couldn't stay in the Q&A session in Google Forms to provide us with feedback. And there will be automatically, once I stop the live webinar, an evaluation form popping up. And I would really appreciate your feedback. Again, from Rotterdam, from me, thank you very much for attending. And I hope to see you soon again in the next webinars. Thank you. Bye-bye.